you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Richard Ross Allen, who will tell us about quantum computing enhanced sensing. So Richard is a PhD student at MIT, advised by Soon-Won Choi. His interest is in learning properties of quantum states and Hamiltonians, and building new connections between quantum sensing and quantum algorithms and complexity. He did his undergraduate study in Harvard in physics, mathematics, and computer science. Oh, free, okay. And previously a student researcher at Google Quantum AI. And currently he's actually visiting Oxford, supported by a Marshall Scholarship. So Richard, the floor is yours.
Great. So thanks so much for the invitation to speak today. It's a great pleasure to be here. Yeah, as Gail said, my name is Richard. Let me go ahead and share my slides for the talk. Okay. Can everyone see?
Yes.
Good. Okay, so great, thanks so much. So my name is Richard, I'm a PhD student at MIT, and today I'll be sharing a bit about our recent work on quantum computing enhanced sensing. Before we get started, I'd like to acknowledge my collaborators on this work. Francisco Machado is an ITEM fellow at Harvard with whom I worked very closely on this project. Isaac Chong is at MIT, Robert Huang is at Caltech and Google, and Soon-Won Choi is also at MIT. Okay, so I think we can all agree that right now we're living through a very exciting time for quantum science and technology, and witnessing really significant advances in all areas of the experimental design of our quantum platforms, ranging from high fidelity operations and gates to the development of logical qubits and circuits, to the synthesis of large coherent arrays of many, many atoms. And as we witness these really dramatic advances in the experimental design of our quantum platforms, I think it's more important now than ever to ask the question, what should we do with these quantum devices? And it would be very ambitious to try and answer that question in one talk, but today we'll tackle one small aspect of this question. So one thing that we can do with our quantum devices is quantum sensing. And quantum sensing at this point is, I'd say, like a very well-established application of quantum technology, which is responsible for humanity's most advanced measurements of really like many physical phenomena. Our most precise measurements of most physical phenomena are now due to quantum sensors. So many phenomena ranging from gravitational waves through LIGO to the development of high precision atomic clocks to measure time, to fundamental physics, particle physics parameters, and magnetic field sensing. And really many, many more physical phenomena are now the highest precision measurements, and in the most extreme scenarios are accomplished by quantum sensors. And what this means is that progress towards better quantum sensing is progress not only towards good quantum science, but better science in general. So anything that we can do to advance the tide of quantum sensing and to develop higher precision quantum sensors that's a boon towards better science. Okay, so at this point, maybe I'd like to take a step back and talk a little bit about the standard setup in quantum sensing, or what people typically would mean when they say quantum enhancement in sensing. So the simplest setting, or maybe the most prototypical setting, is a single quantum sensor detecting a time-independent field. So for instance, let's imagine that there is an unknown magnetic field of strength B, and let's say that we know the basis in which it couples to our spin. So perhaps it couples in the Z basis. And our goal is to estimate the strength of this field B to very high precision. And if you have a quantum sensor that evolves under this Hamiltonian, then there's a pretty simple thing that you can do to measure the magnetic field. You prepare the sensor in the plus state in the Bloch sphere, you let it evolve, and then you perform a measurement, and then you use the classical statistics from this measurement to construct an estimate of the field strength B. And if you do this, one of the standard measures of performance in quantum sensing is known as the sensitivity, B min, and it sort of corresponds to the minimum detectable field strength using a quantum sensing protocol. And so B min for this protocol, it scales like 1 over the sensing time. And the reason for that is that this angle of phase accumulation, is like B times T, that needs to be order 1 in order for this measurement to detect with substantial probability that evolution has occurred. And this resolution on the sensitivity, 1 over T, is actually like the fundamental limit for the minimum field strength that you can detect using a single sensor protocol. But that's not all that you can do in quantum sensing. And in fact, like a lot of the results in quantum sensing have to do with if you have many, many particles, so many sensors. And so if you have many sensors, one thing that you could do is let them all evolve individually under this magnetic field and run this single sensor protocol n times in parallel, and then just measure one by one each of your quantum sensors. And if you do that, your sensitivity improves, and then you just average the results. And if you do that, your sensitivity improves by a factor of root n, just due to addition of many independent random variables. And this is often known as the standard quantum limit. But like one of the sort of key results in quantum sensing, and this is what people typically mean by quantum enhancement in sensing, is that this is not the fundamental limit to how precisely you can measure a magnetic field using n sensors. And if you've heard anything about quantum sensing, maybe you've heard about this Heisenberg limit, which says basically that if you prepare your sensors in some entangled state, then it's possible to measure at higher precision. And so in particular, if you prepare the sensors in this scenario in what's called a GHZ state, then the resulting state sort of acts like a sort of large effective sensor, large effective spin, which has a collectively enhanced coupling to the magnetic field. And as a consequence, sort of the resulting state vector you can imagine is processing on some large effective Bloch sphere, and at a rate which is n times faster. And so as a result, the sensitivity actually improves by an additional factor of root n over the standard quantum limit. And this is known as the Heisenberg limit for quantum sensing. And it's actually, this is sort of the fundamental limit on sensing in a fixed time t and with a fixed number of sensors, the minimum strength magnetic fields. Okay, and that's all very good and well. And the separation between standard quantum limit and Heisenberg limit has been, I would say, like the main driver of focus and progress in quantum sensing. It's led to many experimental and theoretical works for achieving the Heisenberg limit in various scenarios. But that will not be the focus of today's talk. We will not be talking about Heisenberg limited sensing, not so much anyway. The question that we want to answer today is if there are other qualitatively different sources of enhancement in quantum sensing. So I mean qualitatively different than collective enhancement due to many quantum particles prepared in some entangled state. Okay. So in order to answer this question, what we're going to do is introduce a new quantum sensing paradigm that we call quantum computing enhanced sensing. And let me just briefly introduce what I mean by that in contrast to this conventional setting that I've just described. So conventionally in quantum sensing, as I just highlighted, it might be possible to prepare some entangled input state, some entangled initial state, but the evolution of the quantum sensors subsequent to this preparation step is in some sense classically controlled. So by that I mean that you apply a sequence of pre-programmed, often single qubit gates, which you can imagine as just being controlled and executed by some classical computer. We want to contrast that with a new setting, quantum computing enhanced sensing, where in addition to an entangled resource state, you can also apply quantum controlled or entangling gates throughout the sensing step. And so then in principle, I mean, you have some small quantum computer which coherently manipulates your sensors, and you can use it to run quantum algorithms, for instance, or to prepare to run entangling gates between the quantum computer, which is used for control, and the sensors, which are used to detect this external signal. And the key question, which we want to answer in this new setting, is basically, can quantum computing be leveraged to improve quantum sensing? Or is this new setup sort of kind of equivalent to conventional approaches in quantum sensing? Is it inherently more powerful, or is everything sort of just equivalent to having entangled initial states, for instance? Okay, and so we're going to try and answer this question today. That brings us to the outline for today's talk. So as I said, for time-independent sensing time-independent fields, the fundamental limit is this Heisenberg limit. And so, in order to explore this question of quantum computing enhanced sensing, we're going to be looking at a different sensing problem, one which is still very physically motivated and interesting. So I'll start by describing AC sensing unless there is a question at this time. Okay, great. Let's move on then. So we're going to be addressing a different sensing problem than time-independent sensing, but it's sort of the sort of the next most natural or next simplest sensing problem that you could ask. And AC sensing is the problem of detecting not just a weak field, but a weak oscillating field or signal as efficiently as possible. So this will be a signal which has not only unknown strength, but also unknown frequency and phase. And so what's the typical setup for some AC sensing experiment? Well, there's going to be some signal source, and the origin of that signal might be of many different physical forms. So for instance, dark matter detection, or some sort of spectroscopic signal, or even gravitational waves. These are all examples of weak oscillating signals. So there'll be some signal source, and then correspondingly, we'll have a quantum detector, which can interface with the signal. We're going to do some degree of quantum processing, maybe using a quantum computer in our new setting. And then the output for the AC sensing problem will be a binary answer. It's a detection output. So either yes, there is a weak oscillating signal, or no, there's not a weak oscillating signal. And that's why we refer to this as a detection problem. Okay, so that's the sort of schematic workflow, but at the end of the day, we do want to prove things and be a little bit more formal while still being physically motivated, of course. And so let me be slightly more precise about the problem that we actually solve. So formally, we're going to be searching for signals of the following form. So they're oscillating signals at a single tone of the form B cosine omega t plus phi, where, as I said, the field strength, the frequency, and the phase, B, omega, and phi, are all unknown parameters. And we're going to assume that the signal, if it exists, couples to our sensors in some known basis. So for simplicity, we'll just take this model, which is the sort of standard model in quantum sensing, and it'll couple to maybe multiple sensors, NS sensors. And as I said, these parameters, B, omega, and phi, are all unknown parameters, but they're not completely unknown because, if they were completely unknown, then this problem would actually sort of take infinite time. And so we need to place some sort of limits on these parameters. And so in particular, the field strength B, it's going to be unknown, but it's at least larger than some minimum sensitivity, B min. The frequency omega is unknown, but it's only unknown within some interval, delta omega, some interval in frequency space. And the phase, on the other hand, that's sort of a meaningless or arbitrary parameter. So we're just going to assume it's completely unknown and arbitrary, anything from 0 to 2 pi. And I should note, these constraints of minimum sensitivity B min and interval of frequencies delta omega, these constraints are, they could come, for instance, from previous experiments, or they might come from theoretical constraints on the model of the phenomenon that we're trying to detect. These sort of B min and delta omega would come from some physical origin for whatever sensing problem that we're trying to solve. And B min and delta omega, they sort of determine the difficulty or complexity of a particular instance of this AC sensing problem. And so we can even formally define the AC sensing problem as a hypothesis testing task to detect if a signal exists with B larger than B min and frequency within delta omega. And the goal will be to do this in the minimum total sensing time, which we're going to denote tau from here on out. And so yeah, we're going to try and solve this AC sensing problem, and our figure of merit will be sensing time, the amount of time that we're exposed to this external signal. We want to minimize it. Okay, so I've framed this AC sensing problem in a sort of very formal and mathematical way, but I want to re-emphasize here that in spite of this formalism, this is actually a very practically useful, and I would argue conceptually important problem. It's practically useful because, as I sort of slightly alluded to on the previous slide, there are many natural problems in physical science that actually resemble AC sensing. AC sensing has been studied within the quantum sensing community for a very long time, and the reason is it's connected to these problems of dark matter detection, spectroscopy, even gravitational wave detection. And there are real experimental groups that are trying to solve some version of this AC sensing problem by sweeping over different choices of parameter B and omega. I would argue that it's also, beyond being practically important, it's also a sort of conceptually important problem. And the reason is it is kind of the next simplest sensing problem beyond time-independent sensing. And so if you're trying to develop a theory of time-dependent sensing or time-dependent learning, you want to understand the fundamental limits to our precision for solving these sensing problems, or understand optimal protocols, this AC sensing problem is sort of an important first step in developing this broader theory. Okay, So as I said, AC sensing is a problem that's been studied for a long time in quantum sensing. And so there are several existing strategies for solving this AC sensing problem. And we'll talk about one of them now as a sort of precursor to our approach. And in fact, we'll talk about an even simpler protocol to begin with, which is a protocol where, or a setting where you actually know the frequency omega. And so what if you know omega? How, if you know the frequency, can you detect the signal? Well, in this setting, there's actually a fairly simple protocol, which is called it's called the CPMG sequence. CPMG are just the initials of the protocol's developer. So I might accidentally say CPMG. This is what I'm going to mean. So the CPMG sequence, it works if you know the frequency of the field. And if you know the frequency of the field, you can just apply pi pulses or X gates, which are resonant with the signal. And so if you do that, then in the toggling frame of the evolution, the signal is actually going to be, the effective signal will be everywhere non-negative in the time domain. So you get a sort of positive signal, and that means that you can do this simple time-independent sensing strategy again, and you get coherent phase accumulation for the entire duration of your sensing step. And so this provides a means of detecting oscillating signals if you actually know the frequency. You can just sort of transform it to a time-independent signal. And the performance of this protocol, the signals that we can actually sense or detect, the sensitivity of the protocol is again going to scale like 1/t by the same analysis as the time-independent case. But now, in addition, there's going to be some bandwidth to our protocol, so some range of frequencies that we can detect. So we can detect not only signals at frequency omega, but also like a Fourier-limited bandwidth of signals which are centered at omega. And so if you were to plot, for instance, the response function of the sensor, what you'd see is that it's peaked at omega, this resonant frequency, but there's some width, which scales like 1/t. Okay, so that's the signals that you can detect if you know omega. What if you don't know omega? So this is the setting for our AC sensing problem more generally. And one thing that you can do, and which is what's actually done in practice today, is you can just sort of sweep the target frequency omega across the full bandwidth. So more specifically, you can take the full bandwidth of frequencies, divide it up into smaller frequency bins of width little delta omega. And then for each one of these bins, you can apply a CPMG sequence whose target frequency is resonant with frequencies within that bin. And just by sweeping the target frequency over the full bandwidth, you can detect any possible signal within the bandwidth. And the punchline here is then if you just sequentially search across these multiple frequency bins, that's one way of solving this AC sensing problem. And what I've described is maybe like an overly theoretical version of the protocol, for simplification of analysis. But in practice, like this is basically what's done by experimental groups that are searching for AC signals. You just sweep your target frequency across the range of possible frequencies. So this is sort of representative of existing or conventional strategies in AC sensing. Okay, so what's the performance of this protocol? Well, we're just going to bootstrap the analysis for the single sensing step. And so each sensing step, we're going to have as many sensing steps as there are frequency bins. Each sensing step has a sensitivity of 1/t and a bandwidth of 1/t from the previous analysis. But now there are many frequency bins, and the number of frequency bins is going to be the full bandwidth divided by the bandwidth of each individual sensing step. And if you were to combine these scaling relations to compute the overall time that this sensing protocol takes, well, it's going to be the number of bins, which is like the number of experiments, times the duration of each sensing experiment, t. And by combining the relations above, you see that the total sensing time scales like this, like delta omega divided by b min squared. And the fact that it's proportional to delta omega, that corresponds to the fact that you're sort of sweeping across the full bandwidth. So it's going to be proportional to the width of that bandwidth. Good. Okay, so this was all for one sensor. If we had multiple sensors, then we could prepare them in some entangled initial states, and we get an improvement in the sensitivity. It improves by a factor of ns by this Heisenberg limit. And the resulting scaling is as follows. And this is the performance of existing quantum sensing protocols for AC sensing. Okay, so I've described everything in one picture, which is you have b min and delta omega which are like fixed parameters that are given to you as an experimentalist, and your goal is to probe all possible signals with strength larger than B min, frequency in delta omega. But there's a little bit of a different picture, which is maybe more similar to what quantum sensing experimentalists might think of, which would be you're not given these parameters ahead of time. What you have is sort of a fixed amount of time, and the goal is to detect signals which are as weak as possible over as wide a bandwidth as possible within this fixed time. So this is more of like a resource-based perspective. And we can also think about the performance of these strategies in this picture, and that would lead to a plot sort of at the following form. So what this plot, you should think of this plot as telling you what signals are detectable within a fixed time tau. And so for any choice of protocol, there's going to be some region of this two-parameter space which tells you which signals are detectable. And like everything to the upper left of one of these curves is going to correspond to a detectable signal, because that's like higher field strengths, shorter bandwidths. And what we see is that by adding in the additional resource of entangled initial states and moving from the standard quantum limit to the Heisenberg limit, that does improve the range of detectable signals by shifting this curve down. But it doesn't really, this is sort of just corresponds to an improvement in the sensitivity. And so it doesn't change the fundamental trade-off between B min and delta omega. And in particular, like the slope of this line is fixed when you add entanglement. So that'll be something to keep in mind as we move forward. Okay, so so far, the discussion has been rather disconnected from our motivating question, which was, can quantum computing be leveraged to improve quantum sensing? It's not a priori clear why this question is connected to the problem that I've described. And so, we'll talk about that now. And so this sort of leads to our first main result, which is that indeed...
Sorry, can I just interrupt? Just to clarify, like, so when you get this improvement when you use these entangled sensors, so
yes,
like, I mean, in some ways, like, you know that the limit is improved, but is it always known how to actually achieve the limit? Or is it?
Oh, yeah, so that's right. So these are not fundamental limits as of yet. This is actually a description of the performance of a particular protocol. And this particular protocol is, you divide your bandwidth into little individual regions and you probe them one by one using, for instance, a CPMG sequence. And this is the scaling achieved by that particular protocol.
Yeah, but I mean, like, for example, when you use an entangled sensor, you have to tell me how to entangle them, don't you?
Oh, yes. Yeah, so that depends on the way in which the signal couples to the sensors. And so if it couples in the Z basis, then the optimal state is like a GHZ state, for instance. But in general, it would depend on the way that your signal couples to your sensors.
Okay, but in any case, it would be known how to do it.
So I mean, if you know the basis in which the signal couples, then it's known what the optimal initial state would be, for instance.
All right.
Okay, good question. And I mean, so I mean, in the time independent setting, you can generalize beyond that and always get Heisenberg limited sensitivity for the parameters of the Hamiltonian. There's like a long series of works that establish this, but in this simple setting, like we know how the signal couples to the sensors, and then the optimal initial state would be GHZ, because that's actually sort of not going to be so much the focus of this work. It's not, I mean, as I said, the goal will be to sort of go beyond improvements that can be obtained just by a well-prepared initial state. Yeah, so that's sort of like not so much the focus of this work, but still good question. Okay, so first main result is that there is indeed a quantum computing enhanced sensing algorithm which solves this AC sensing problem more efficiently than the existing approaches. And so the scaling of our approach is going to be like 1 over B min or NS B min times the square root of delta omega over NS B min. So if you compare this to the scaling of the existing strategy, what we see is that the difference is you get a quadratic improvement in this delta omega over NS B min. And that improvement you should think of as being like quite large in settings of interest. So the setting of interest is very weak signals and like a lot of uncertainty in the frequency, so very large bandwidth relative to the signal strength. And so in that setting, like delta omega over B min is some very large number, and we get a quadratic improvement in that very large number. And this algorithm we call quantum search sensing for reasons that will become clear, or perhaps they already are if you're if you're paying attention. but yeah, we'll describe that next. Okay, so there exists a protocol which achieves the scaling. Oh, and yeah, one other technical note. So this O tilde, that means up to polylog factors in delta omega over ns bmin. So this is standard notation in algorithms. This O tilde. Right, so there exists a protocol achieving this performance. And our second main result is that it is in fact optimal. So in fact, like any quantum computing enhanced sensing algorithm, even a protocol which has an infinite sized quantum computer and can apply like infinitely many, infinitely fast gates, any such protocol must take a total amount of time which scales like the previous result. So in fact, like what this means, we call this lower bound the Grover-Heisenberg limit. So you should think of it as sort of an extension of the Heisenberg limit to this AC setting. And what it means is that our QSS quantum search sensing algorithm is in fact optimal for the task of AC sensing up to these polylog factors. Okay, so the name Grover-Heisenberg limit is perhaps suggestive, but yeah, we'll talk about that very soon. Okay, and we can look at our diagram of detectable signals now and see what improvement we get from this quantum computing enhanced sensing approach. And what we see is that in fact, like a new region of this sort of phase space is unlocked. So there are new signals which can be detected if you have the additional resource of quantum control, which were not detectable using these existing strategies. And moreover, like the scaling of this line, I mean, this is in log space, right? And so the slope of these lines, that corresponds to the power law in the trade-off between Bmin and delta omega. So the separation gets like better and better as the unknown parameters become, as sort of delta omega gets larger, that sort of thing. So there are new signals which were fundamentally undetectable before and which are now detectable using a quantum computer as a control resource. Moreover, because of our second main result, this performance of this quantum search sensing algorithm is essentially optimal, and any other signals are just impossible to detect. And so, basically this like pins down the question of what signals are detectable within a fixed total time, which ones are not. Okay, good. So that takes us to the end of this sort of like intro and motivation. And now we can talk about the actual algorithm, unless now would be a good time if there are any questions. Okay, if not, let's move on. So recall the existing strategy that we described previously. The punchline there was that if you search sequentially across multiple frequency bins, you can solve the sensing problem. And the keyword that we want to hone in on here is searching. And the reason is, if we have this additional resource of a quantum computer, well, quantum computers are good at solving unstructured search problems. This is Grover's algorithm. And so our perspective is going to be, if we can take this sensing problem and sort of map it into a computational problem, a search problem, then we can leverage existing algorithmic improvements for this computational problem, which in this case is search. And you might imagine this is actually like a more general framework or blueprint for mapping sensing problems to computational problems and then solving them using quantum enhanced algorithms. And we'll talk about that perspective a little bit later. But yeah, for now, our goal will be to leverage sort of quantum speedup for search. Okay, this next part is sort of just, we'll just briefly review what's meant by a search problem, but I'll go, maybe speedily through this. So a search problem can be described in the following sort of toy way. Given n identical and otherwise unmarked boxes, the goal is to find some special or marked box. And classically, sort of the best or only thing that you can do is just query these boxes one by one until you find the actual marked box, which we're going to denote k star moving forward. And classically, if there are n total boxes, then this is going to require like a linear number of queries. I mean, you can get a slight improvement if you just like randomly select your boxes, but it's always going to be like a linear number of queries. And the very surprising and remarkable fact is that quantum mechanically, there is in fact an algorithm which requires just like square root of n queries. This algorithm is known as Grover search. But we should maybe slow down, be a bit more careful, and explain what it means to query quantumly. Like what exactly do we mean by that? So in the quantum setting, each of these boxes is going to be represented by some distinct quantum state of our quantum computer. So if there are n states, n boxes, then there's going to be like a quantum computer of log n qubits that we use to encode these various states. And by query quantumly, what we mean is that we apply a so-called quantum oracle. And so the way that the quantum oracle works, it sort of is a way of checking the identity of these boxes in superposition. And so the quantum oracle, the way that it works is you feed it a state k, which represents one of these boxes, and then it will mark that state with a phase if and only if it is the marked state, or the state which is like uniquely identified. And so if k is equal to k star, we'll mark it with a -1 phase. Otherwise, we do nothing. And then the quantum oracle works in superposition as well. So we extend by linearity. And this is what we mean by quantum queries. We mean calls to this quantum oracle. And so Grover's algorithm can solve the search problem using just a square root number of queries to this quantum oracle. Okay, so this is in the sort of conventional like oracle framework for search. If we want to leverage this Grover speedup for search, then we're going to need to design some sort of equivalent sensing oracle, which acts in the way that the regular quantum oracle does. And so the main challenge will actually be designing this sensing oracle using just the time-dependent dynamics of our external signal. Okay, so the sensing oracle, so the different states are no longer going to be boxes, but these states will correspond to the different frequency bins, possible frequency bins in which the signal frequency lies. So the number of bins is going to be scaling like delta omega over b min, as we saw previously. And each one of these bins will correspond to a distinct state of our quantum computer. And the role of the sensing oracle will be to basically like transduce the external signal from the sensor, which interfaces with the signal, which interfaces with the natural world, to transduce that signal into the quantum computer. And then we can leverage like Grover's algorithm, for instance. And the way that the sensing oracle should work, well, on the quantum computer, it should work in the same way that the regular quantum oracle does. So it should mark with a -1 phase the state k, such that the state k star, such that the signal frequency belongs to bin k star, and otherwise it should act as identity. And on the quantum sensor itself, the quantum sensor should return to its initial state at the end of the sensing oracle. So even though the quantum sensor might be entangled with the quantum computer sort of during the middle of the sensing oracle, at the end it should be decoupled from the quantum computer. And the reason is that we're going to have to run the sensing oracle multiple times, and there can't be any residual information about the signal like stored in the sensor at the end of the sensing oracle. And the upshot is that if we can only engineer the sensing oracle, then we can just use it to run Grover's algorithm and solve this AC sensing problem with a square root n speedup. And if you look at the scaling of n, delta omega over ns b min, well, this square root speedup that's exactly the speedup that I described in our results slide. Okay, so that's good. And I would say that up until this point, once you realize like AC sensing can sort of be viewed as a search problem, up until this point, you can sort of just follow your nose and say like, okay, well, if we want to run Grover's algorithm, we're going to need some sort of sensing oracle which acts in this way. You can kind of like get to this step just by sort of like following like the natural sequence of deductions. But once you get to this step, things are it's a little bit unclear how you would actually engineer the sensing oracle, because it acts very differently to regular quantum sensing protocols. So I mean, the AC signal, it depends on a bunch of unknown parameters. And for every value of those parameters, we're going to need to engineer this like exact, perfect, discrete sensing oracle. And so, we'll now talk a little bit about the challenges in engineering the sensing oracle. And the rest of the talk will be like basically, how do you engineer the sensing oracle? Okay, so I'll describe now, as I said, some sort of key features of the sensing oracle, which make it different than conventional sensing approaches. And then we'll resolve those challenges. So one of the first differences, which we see, is that the sensing oracle should be capable of sort of sensing in superposition in some sense. So let's return to the regular CPMG sequence that I described previously. And in the CPMG sequence, you apply pi pulses at some particular resonant frequency, and then your quantum sensor has a response only at that frequency. So the response of the sensor is like peaked at one frequency that corresponds to the resonant frequency of your pulses. By contrast, in the sensing oracle, we sort of need to engineer like a conditional response of the sensor. So conditional on the state of the quantum computer, we want our quantum sensor to be sensitive to frequencies which are in different bins. So if the quantum computer is in state 0, for instance, then our sensor should be sensitive to the very first frequency bin. If it's in the 1 state, it should be sensitive to the next frequency bin, so on and so forth. And this sort of sensing and superposition behavior, I'll argue to you that it's actually not difficult to accomplish. This sort of will not be the bottleneck in designing the sensing oracle, but it's important to point out anyway. And so one simple thing that you could do to realize the sensing and superposition behavior is just apply the CPMG sequence conditionally. So conditional on the state of the quantum computer will apply a CPMG sequence at a different resonant frequency. And this will engineer this like sensing and superposition behavior. So that's not the bottleneck. The more difficult challenge is what we call digitization. And so maybe to motivate why we need digitization, let me discuss like a sort of specific example, again related to the CPMG sequence. So as I said previously, CPMG sequence, what it does is it sort of creates an effective signal in the toggling frame, which is everywhere non-negative, and then we can measure that using time-independent sensing. But what I didn't point out at the time is that actually this diagram sort of assumes a particular phase relationship between your CPMG sequence and the unknown signal. And in particular, like if the phase of the unknown signal is shifted, then the effective signal might still average out to 0. And this signal would then be undetectable because it averages to 0. And that's an issue in our setting because the phase of the magnetic field is in fact an unknown parameter. Okay, so there are simpler ways in the conventional setting to resolve this unknown phase issue. You can just wait for random time at the start of the protocol, and then with high probability, with like constant probability, the phase will be such that you can still detect the resulting signal. So this is sort of like not, this specific problem can be resolved more simply. But my goal is not to point out like this specific issue, but rather to point to a more general characteristic of conventional sensing protocols, which is in contrast with the way our sensing oracle should work. And so specifically, in conventional sensing protocols, the response of the sensor is sort of highly sensitive to variations in these unknown parameters b and phi. And that is by design, because conventionally in quantum sensing, the goal is to detect small fluctuations in these unknown parameters and to estimate these parameters with very high precision. And so you want the response of the sensor to be very sensitive to perturbations in the unknown parameters. By contrast, the way that our sensing oracle should work, it should have like a sort of discrete or digital response. So for any field strength larger than b min, and for any value of this unknown phase, the sensing oracle should produce like the exact same discrete response, like a pi phase flip if the frequency is in the right bin, and like 0 like phase rotation otherwise. And so it'll really be like this discrete digital response, which is challenging to engineer in the sensing context. And I want to argue that this is sort of not like a quirk of our protocol, but it's in fact a crucial challenge to overcome if you want to interface quantum sensors with quantum computers. Okay, and I'll have like a little bit of theory to back that up in just a second. Okay, so this has been like mostly motivation and an illustration of the challenges. I'll now take a couple slides to actually concretely describe the way that we construct the sensing oracle. And there's going to be 3 elements. The first is phase agnostic sensing, which resolves this unknown phase shift challenge that I described previously. The second will be sensing and superposition, and the third will be nonlinear signal processing. Okay, so let's begin with phase agnostic sensing. And these next couple slides will be sort of like the only like technical slides in the talk. They'll be sort of the one where we actually do some math. And so, if I say something that's poorly explained, like please just interrupt me. Okay, so our goal is to engineer the sensing oracle, but as an intermediate step, we're going to engineer something that we call an elementary sensing unit. And this is going to be like a conditional rotation of the quantum sensor. So ZS indicates the quantum sensor. conditional in the state of the quantum computer. And the angle of phase rotation, well, it's not going to be precisely known at first, these conditional angles, but we're going to demand that they be independent of phi, the phase of the magnetic field. And the reason is that, I mean, the phase phi sort of encodes like the time-dependent nature of the signal. And so if we can engineer a response which looks like this, a phase-agnostic response, then that gives us like a black box, which we can query multiple times with the assurance that it's actually sort of acts identically regardless of the phase of the magnetic field. Or it sort of eliminates the time-dependent nature of the field in some sense. And the way that we're going to engineer this is using AC Stark shift, which is sort of a core like principal phenomenon in quantum optics at AMO physics. And the way that AC Stark shift works is as follows. So initially, like this is the Hamiltonian, which describes our sensor. So it's two-level system, which couples to some AC field at a frequency omega. And let's imagine that we add a time-independent control field, which is detuned from omega by an amount delta zero. Then the Hamiltonian looks like this. And if we look at this Hamiltonian in the rotating frame, a frame which rotates at frequency omega, what we see is that it's now a time-independent Hamiltonian of the following form. And the key feature of this time-independent Hamiltonian is that it has eigenvalues which don't depend on the phase phi. So phase-independent eigenvalues. And what that means is that if we look at dynamics under this time-independent Hamiltonian, well, it's just Larmor precession. And the angle of phase rotation, regardless of the phase of the magnetic field, is going to be independent of the phase phi, because the eigenvalues are independent of the phase phi. And so this is good. It's sort of a step in the right direction. We get an angle of phase accumulation which doesn't depend on phi. The issue, though, is that because the axis of rotation depends on phi, the final state of the sensor will too. And we need to eliminate that dependence as well. And the way that we can do that is by adiabatically ramping the coupling between the sensor and the signal. So here, chi of t is some adiabatic ramp, which starts off at 0, ramps up to 1, and then ramps back down to 0. And if this adiabatic ramp is sort of like slow enough or satisfies some smoothness characterization, then the resulting dynamics on the Bloch sphere is, well, initially the adiabatic ramp is 0, and so the effective Hamiltonian is along the z-axis, and so our sensor starts on the z-axis, and then it sort of slowly rotates out, and the sensor follows it, and then it'll slowly rotate back, and once the adiabatic ramp is 0 again, the state has returned to be parallel with the z-axis. And as a consequence, like the state at the end of this evolution is also independent of the phase phi of the magnetic field. And this is exactly what we wanted. We wanted a phase response, a response of the sensor which was independent of this magnetic field phase phi. So this accomplishes phase agnostic sensing. Okay, so that's good. That's sort of the first step. This was all for a particular target frequency omega 0, which you should think of as being like corresponding to a particular bin in the frequency space. Ultimately, we want to do sensing in superposition. And at the level of theory, it's sort of simple to engineer that response. We'll talk about in practice how you would actually engineer this in a bit. But at the level of theory, we could just change this control field to an omega k, which is then conditional on the state of the quantum computer. So we apply like a conditional control field on the state of the quantum computer. And again, it's actually very simple in experiments to engineer this kind of like conditional control field. And I'll describe that in a couple slides. Good. And so this basically engineers this elementary sensing unit that we wanted. And what about these phases phi k, these rotation angles phi k? Well, they correspond to the dynamical phase under the adiabatic dynamics. And we don't really need to know precisely the details of these phase angles. These phase angles, they're just the integral of the time-dependent eigenvalue of the Hamiltonian. We don't need to know their exact dependence on B and delta, but the important thing will be that this rotation angle theta k is going to be largest when k is equal to k star. So why is that? When k is equal to k star, then the frequency of the unknown signal belongs to the k star bin. And so that means that the detuning between the control field and the external field is smallest. And because these phase angles are inverse in this detuning, it's going to be largest when k is equal to k star. So that's sort of like, that's good because we want some way of differentiating the marked bin from all other bins. And the way that we're going to do that is, well, the phase accumulation is largest. Okay, so now there's just one more ingredient to engineer the sensing oracle, and that's some element of like nonlinear signal processing. So to explain that, let's sort of return to this digitization picture. And the spirit of digitization was to take sort of continuously varying, or in fact, like linear response, linear in B, and to map it to a sort of discrete or nonlinear response of the sensor. And we're going to need to accomplish that now. And so the key question is, how can we engineer these nonlinear transformations in a quantum mechanical way, despite the fact that quantum mechanics is a linear theory? And the good news is that we don't need to invent from scratch a protocol or a framework for doing this. There's actually an existing algorithmic framework called quantum signal processing, which accomplishes these nonlinear transformations. And QSP, or quantum signal processing, it's a very like well-developed area at this point. It's like responsible for a lot of advances in algorithms, like Hamiltonian simulation especially. But here we're going to just introduce like the bare bones, like simplest ingredients that you need to understand QSP. So the setting in QSP is there's some signal unitary, which is a rotation by an unknown angle theta. And we repeat that signal unitary multiple times, and we interleave it with these optimized control unitaries, which are rotation about an orthogonal axis, so like the x-axis in this case. And these control angles, phi 0 up to phi L, these are angles that we control as the experimenter. And the goal is to engineer some effective rotation by an angle f of theta, which depends on the control angles. And here f of theta is in general some like programmable nonlinear function. And so the way that it works is if you want to engineer a nonlinear transformation by f of theta, what you do is you take f of theta and then you compute the optimal angles phi 0 up to phi L, and you execute this QSP sequence. And so now the problem of engineering nonlinear transformations amounts to just choosing the right function f. And so for our setting, the f that we need, we can determine it in the following way. So what we have is a conditional rotation of the sensor where the rotation angle is like largest for the marked state. And what we want is a conditional rotation where the phase angle is exactly pi, so that's a phase flip, when k is equal to k star, and exactly 0, so axis identity, when k is not equal to k star. And so we want to basically amplify these large phase angle theta k star up to pi, and we want to suppress all other phase rotations down to 0. And so for that, the right function f is in fact a step function. So it'll amplify these large phase angles, and it'll suppress all the small phase angles. And by engineering, so if you use like a good approximation to the step function, and we use that to design our QSP sequence, this exactly performs the nonlinear transformation that we want and completes the sensing oracle. Okay, so that was like a good bit of detail, but what I've given you is actually like a very like accurate and complete description of the way that you engineer the sensing oracle. So this was really like all the details. So now you actually hopefully understand the construction of this like digital sensing oracle, and this is the key step. Once you have it, you can just run Grover's algorithm and achieve the square root speedup. Okay, good. So I know we're running like a little bit short on time, but these next couple sections are like super quick. So if there's any questions about the actual quantum search sensing algorithm, now would be a good time. Otherwise, I'll talk about some more like sort of broader perspective or motivation for these results. Okay, great. So now I'd like to talk like a little bit more generally about this like computational sensing framework, because I've described, like by some might argue that like the approach we've taken is like a little bit complicated. It's certainly more complicated than the like existing strategies, and it uses a quantum computer and it engineers this like digital nonlinear transformation. And you could ask rightly, like, is this necessary, or is it fundamentally different than like what's conventionally done in quantum sensing? That was sort of our motivation, is to do something fundamentally new. And what I'll argue now is that this approach actually is qualitatively different, and that the enhancement that we achieve arises from the use of quantum computation, and not, for instance, like it couldn't be achieved just with entangled initial states, for instance. And the way that I'm going to argue that is by considering classes of quantum sensing protocols, which in some sense like encapsulate existing or conventional approaches, and proving lower bounds on the amount of time that these classes of protocols would take to solve the AC sensing problem. And the first class of protocols that we consider are what we call QFI-based protocols. So the QFI, or quantum Fisher information, is sort of like the standard measure of performance in quantum sensing. So the QFI tells you something about like the sensitivity of your quantum sensing protocol to very small perturbations in these unknown parameters, like B and omega, for instance. And conventionally in quantum sensing, like having a large quantum Fisher information is basically like equated to being a good sensing protocol. And so if you come from a quantum sensing background and you wanted to design a protocol for AC sensing, well, like one thing that you might do is just try and optimize the QFI and the sensitivity to this field B across the full bandwidth delta omega. And that's basically how we define a QFI-based protocol. It's a protocol which distinguishes perturbatively small b from signals of strength b min just by maximizing QFI across the bandwidth. And you might think that this would be like, you know, a decent approach to solving this AC sensing problem. But what we prove is that, in fact, any one of these QFI-based quantum sensing protocols must take a total amount of time that scales, you know, as follows. So this is like a lower bound on the sensing time which any of these protocols would take. And you know, notably, like this scaling is the scaling of the like existing or conventional protocol, which I described at the beginning. And so it's worse than the scaling of our protocol. And what that means is really like, in order to achieve this fundamental Grover-Heisenberg limit, a non-perturbative approach is necessary. So it's not sufficient to just like optimize the QFI and take the route that conventional quantum sensing protocols take. And maybe from like a broader moral perspective, what this means is that quantum Fisher information, which has for a long time been like the standard measure of performance in quantum sensing, is in fact, you know, at least for this problem, it's of limited use as a diagnostic for like performance in sensing. Okay, we also consider, you know, a couple other classes of protocols. One other which I'll highlight here is what we call classical signal processing protocols. And a classical signal processing protocol is one, you should think of it as being like the only way that you can modulate the interaction between the sensor and the field is by applying some filter function to the sensor. So sort of like controlling the like amount or degree of interaction between the sensor and the external field. And so these are protocols which are equivalent to applying some effective Hamiltonian, which looks like this, with a different filter function for every sensor. So these chi-IFT, they're sort of like arbitrary functions which modulate the interaction between the signal and the sensor. And these protocols are actually like equivalent to like the CPMG sequence, for instance, and like a lot of other AC sensing protocols. They can be framed in this way. And what we prove is that also like this class of protocols obeys the same lower bound. And what this means is that like an intrinsically like nonlinear approach is necessary. And so like the combination of these qualities, like being non-perturbative, being nonlinear, we also prove that you need like a certain amount of like coherence time. You need to be able to do coherent quantum evolution. Like all these features together, we think point strongly to the necessity of some amount of quantum computation in order to achieve this fundamental limit. Okay, so I know like we're running a little bit low on time. I've got one or two slides on near-term experimental implementations of this protocol. And so if we have the time, I can discuss that. Otherwise, we could proceed to the discussion and outlook. So do we have maybe a couple more minutes?
Yeah, I think like 5 minutes is fine.
Great. Yeah. Okay. Yeah, we'll definitely wrap up by.
Mm-hmm.
Okay, good. So we've been living in theory world for a while, talking about optimal protocols, lower bounds, etc. But at the end of the day, we also want to to see this kind of quantum computing enhanced speed up in practice or in experiment. And so now I'll briefly describe some promising numerical simulations of a near-term implementation of this protocol. And so let's step back slightly and ask, what are the actual experimental requirements to run our protocol? So for one, we need arbitrary rotations of our sensor. So let's imagine it's just one sensor for now. We need to be able to do arbitrary X rotations in order to achieve, in order to do QSP. Okay, so that's just one sensor. So we just need arbitrary rotations of one sensor, single qubit. We also need global rotations of the computational qubits. So that's like the same gate applied simultaneously to all our computational qubits. And so that's simpler than like individual, like single site control of the computational qubits. And then the final thing that we need is some way of coupling the sensor to the computational qubits. And it'll turn out that Ising interactions are sufficient to engineer the dynamics that we need. And let me explain that a little bit more. So, why are Ising interactions enough for the interaction that we need? So like this is an example of an Ising Hamiltonian, which couples one sensor, ZS, to NQ computational qubits. And so there's like whatever the bare frequency of the sensor is, that's the first term. And then we have Ising couplings with strength Ji. And this Hamiltonian is written so that the sum is over like different positional indices of the computational qubits. We can rewrite it. So now the sum is over the different states of the computational qubits, ranging from 1 to 2 to the NQ. We can rewrite it in this form, where now these couplings omega k are like the signed linear combinations of the Ising couplings Ji. And this form of interaction, the sort of like conditional splitting of the sensor, that's exactly the kind of interaction that we needed in order to engineer the sensing and superposition. So this is the conditional control field that I was describing previously. So actually, like this kind of interaction, this Ising interaction, is all that we need in order to implement our like phase agnostic sensing and like sensing and superposition. And so pictorially, we have a picture like the following. So conditional on the state of the quantum computer at the bottom, you have a different sort of like effective splitting of the quantum sensor. And then the marked frequency, omega k star, is just whatever splitting is closest to the unknown frequency of the magnetic field, omega. Okay, good. So Ising interactions are enough. And that suggests that maybe, because Ising interactions are sort of the most ubiquitous interaction in nature, that suggests that maybe a near-term experiment could be possible. And so we analyzed a proof of principle experiment in our work using an NV center platform. So NV centers are sort of one of the like best studied and most established like platforms for quantum sensing. And there are two different qubit degrees of freedom in NV centers. So there's an electron spin, which is a very good sensor. And then there are nearby C13 nuclear spins, which are much longer lived and can therefore act as computational qubits. And we do numerics for a sort of simplified version of our problem, where actually like the field strength B and the phase phi are known, and the frequency omega belongs to some discrete set, just to sort of get like a proof of principle understanding of the speedup which is available. And in the simplified setting, actually like the sensing oracle execution is much simpler because it corresponds to just the 2 pi rotation of the sensor at a frequency which is whatever the discrete omega k star, whichever of the discrete frequencies is the unknown frequency. And so the simplified setting, we perform like very accurate, like as accurate as possible numerical simulation using realistic values of the decoherence, realistic values of the coupling strengths, number of available computational qubits, et cetera, like our closest approximation of what would actually be possible in an experiment. And we compute this improvement factor, which is the ratio of conventional quantum sensing time to our quantum computing enhanced sensing time. And the takeaway, I won't go through these results in detail. You can look in the paper if you're curious. But the takeaway is like for realistic values of these various experimental parameters, we think that we could see like a factor of 4 or 5 improvement in sensing time. And so that we would hope will be like visible in an experiment as a demonstration of quantum computing enhanced sensing. Okay, so we're running close to the end now. So let me conclude with just a little bit of perspective and outlook, and then I'd be happy to take any questions. So what's next for quantum computing enhanced sensing? Or maybe like what are the most valuable perspectives? One perspective on this work, which I like, is it comes from thinking about the oracle framework in quantum computing. So the oracle framework in quantum computing is sort of like the only setting where we have provable separations between classical and quantum computation. But there's sort of a common complaint about the oracle model, which is that you need to be given this oracle as a black box. And so it's not clear like where it comes from, who gave you this oracle, etc. And one perspective on this work is that it provides a way of sort of unlocking this black box by realizing oracular dynamics from physical time evolution. So physical dynamics of actual, real world behavior. And that provides a way of realizing these oracular dynamics. And it's actually like very natural that quantum sensing would translate to an oracular framework, because it's all about, you're interfacing with some dynamics, but you don't exactly know a description of those dynamics. So a very natural question that comes from this perspective is whether or not larger oracle speedups in the oracle model might lead to greater metrological gain. But you want to be careful the way that you do this, because similarly to how AC sensing was like a physical and interesting problem for quantum sensing, we'd like these larger oracle speedups to correspond to like interesting physical problems as well. A different, so maybe like another perspective or future direction is in the design of logical or error-corrected quantum sensors. So our classical devices, for instance, interface with all kinds of sensors. So I mean, the keyboards and video cameras that we're using today, these are all examples of sensors which couple our classical computing devices to the external world. And there are a lot of sort of like pessimistic results about interfacing quantum error correction with quantum sensing. And one hope is that maybe like some of these digitization techniques could beat some of this conventional wisdom and lead to error-corrected sensing and the next generation of quantum computers which interface with quantum sensors. Okay, so that is all from me. Thank you all so much for your attention and interest, and I'd be happy to take any questions now.
Right. Thank you very much. That was a very wonderful talk. Yeah, so I guess anyone in the audience who has questions, please feel free to unmute yourself and just ask right now. Okay, so maybe I can start first. So just sort of like I'm just thinking like, if you describe sort of like the protocol, if you kind of can do things really well, right? So I guess like my question is like, how are the results affected if things are noisy?
Right. Yeah. So I mean, this is an extremely practically important question, right? But I think a little bit of there should be hope that comes from our proof of principle experimental results, because these are done at finite decoherence and like for actually pretty realistic values of decoherence times in like an NV-centered platform. And what we see is that the performance of our protocol over the best classical protocol, there's actually like a sort of a finite limit to noise that we can tolerate. Even without any error correction, we can tolerate noise up to a certain limit. So there's more discussion of this in the paper, but actually there's like even up to a finite error rate, the performance of our protocol can like exceed or like improve upon the best like conventional strategies as well. That's even without error correction. So there's like a little bit
you can do further, like it works better, of course, if you also include error correction.
So actually, like this is sort of a very interesting question and sort of an open question, because as I sort of alluded to a little bit, there is kind of a tension between quantum error correction and quantum sensing. And so, I mean, if you error correct out your noise, then you also error correct out very weak signals. And so this is why there's like a little bit of like, in fact, like, I mean, one of the common like arguments for quantum sensing is, oh, if our quantum devices are so sensitive to external noise, like, can't we just use them as a sensor for noise? Like, so in some sense, like typically like this sensitivity is described as an advantage in quantum sensing, but in our setting, if we're trying to isolate our quantum sensor, then it's, again, a disadvantage. And so actually, I would say that it's still an open question, the extent to which error correction and sensing can be combined. And so that's, I think, like a very interesting area for the work.
Okay. Yeah. Okay. Thank you very much. I probably should let other people the opportunity to ask questions.
Yeah. No, we've ran a little bit over, so hopefully there's been a bit of attrition.
Yeah. Hi. So yeah, I might be missing something, but so I'm a little bit curious about what you say. You're transforming a sensing problem to a computation problem. Yeah, can you maybe elaborate more on on a high level? What's that? Yeah, I'm not very familiar in this field, so yeah, I would just want to get a high level point on what's this concept.
Great. Yeah. So I mean, the high level perspective is, most focus in quantum algorithms research is centered around, computational problems. So, the input is some bit string, the output is some binary answer, for instance, and the fundamental building blocks are like maybe discrete quantum gates or those sort of discrete transformations. And we have a number of quantum algorithms, for instance, in the Oracle model, which exhibit speedups over the best classical approaches. So search is one example. There's also, there's a whole wealth of like quantum speedups in the Oracle model. And so the broad perspective would be if there's some way of viewing a sensing problem as, if the discrete version of a sensing problem can be viewed as a computational problem for which there's a known quantum speedup, then by taking some of these digitization techniques and sort of transforming like continuous time dynamics to like discrete like gate-based dynamics, then we can leverage these quantum speedups. And so for AC sensing, turns out like very naturally this problem maps to a search problem. And so we do all this digitization and such to map like the continuous search problem to a discrete search problem, and then leverage a quantum computation.
Okay.
So yeah, the broad perspective would be like, trying to build more connections between the sensing problem and their sort of discrete corresponding like computational problem.
Yeah, also another question on the problem settings. So you say it will tell you that when you find the signal, but you don't know the parameters of the signal. So
yeah, that's another good point.
Like,
so
it either exists or not, like.
Right. So the version that I've described is like this sort of very discrete like hypothesis testing version. But actually, like our algorithm has a certain amount of tolerance to it. So what that means is that in addition to just differentiating between signal, yes signal, no signal, you can actually differentiate between yes signal within some tolerance or no signal like outside of some tolerance. And so you can use this. You can imagine like you could do a binary search, for instance, over the full range of frequencies to get higher and higher precision estimates of the parameters of the field. And eventually, you would sort of exceed the tolerance of our algorithm, and you have to switch to existing optimal, like high precision quantum sensing algorithms for estimating the frequency, for instance. But you could use, there's a degree of tolerance to our algorithm which allows you to solve more than just this like super discrete version. And you sort of like, like you should think of like binary search sort of.
Yeah, thank you.
Yeah, thanks so much for the question.
All right. Yeah, okay. I mean, like, I actually kind of like the question, because I was going to ask, like, because you only know like whether it's sort of like, is it like effectively zero signal or above some beam in, but in some sense you could actually sort of like run this thing first, and then once you figure out what this kind of beam in is, then you can do other things if you wanted to really pin down what the actual value is.
Exactly. Yeah. So you should think of this as maybe like even just sort of like a first step in the parameter estimation framework. And oftentimes, like it would be honestly like sufficient or like a good first step to just answer this discrete version. So I don't know, dark matter detection, for instance, would be, we don't even know if like this model is correct, if like the axion is the correct candidate for dark matter. And so the first question you want to ask is there any signal at all? And then afterwards, you can try and like estimate these parameters more accurately. So yeah, you should view it as like a starting point for parameter estimation.
At least you know that there is signal existing in some range, right?
Exactly. Yeah. So you get like very discrete information at first, and then you can narrow it down subsequently.
Right. So is there anyone else with questions? Yeah, I guess like some people have kind of scattered away. So I just wanted to clarify something about so because you have to decide on the number of bins, right? I guess like in your case, you're already fixing it to be the one that will give you the optimal one coming from what you know about Grover search, right?
No, so the number of bins is determined by the trade-off between bandwidth and sensitivity. So it's for a particular value of the sensitivity Bmin and the bandwidth delta omega. That actually like determines the number of bins. It's just the ratio of those two.
Okay, I see.
So it's set by like each you should think of it as like each call to the sensing oracle needs to take a time which is like 1 over Bmin, because that's the amount of time that it takes to detect the signal in one sensing step. And so that basically that sets the number of bins.
And okay, if I understand it correctly, then, and also that means there's really no advantage in not uniformly spacing the bins.
Yeah, actually, I mean, the binning strategy that we need to employ is actually like slightly more complicated than I illustrated. But yeah, I mean, if it's like a uniform prior over the possible values of the frequency, like right now we've assumed it's like the frequency is completely unknown. It could be any value.
Okay.
And so therefore, like in that setting, there's no advantage to like spacing the bins differently. But if you had like a non-uniform prior over possible values, then it might be better to change your binning strategy.
Bias the
Yeah, you could maybe like bias some aspects of the protocol. Yeah.